Okay, good morning. Today, my topic is speed control methods, rotor side. Speed control methods, rotor side. It comes under the module number 2, starting and testing of three-phase induction motor. We know that the speed of the induction motor can be controlled by basically two methods, from stator side, from rotor side. In stator side, there are four methods. One is supply frequency control to control the speed. Second one, supply voltage control, controlling number of stator poles. Fourth, adding rheostat in stator circuit. So these models we already discussed in the last lecture. And from rotor side, there are three methods. The first method will be the adding external resistance. Second method is cascade control. Third method is injecting slip frequency voltage into the rotor circuit. Injecting slip frequency voltage into the rotor circuit. Now we'll see one by one. First one is adding external resistance in the rotor circuit. From the torque equation of an induction motor, we know the torque is directly proportional to S E2 square R2 by R2 square plus S X2 whole square. Okay, R2 will be the rotor resistance per phase and X2 will be the rotor reactance per phase at running condition, and E2 will be the E2 square will be the rotor EMF per phase, rotor EMF per phase during running condition. For low slip region, this inductive reactance, okay, that is the slip reactance, is very much lesser than rotor resistance. So Sx2 can be neglected, and for constant supply voltage E2 is also be a constant. So therefore the torque is directly proportional to SV square R2 divided by R2 square R2 by R2 square. Now here the R2 and one R2 will be cancelled. You will get S by R2. Since the voltage V is constant, so we have to neglect that V and S by R2. So if the rotor resistance is increases, okay, if the rotor resistance this will be increases, then the torque produced will be decreases. But when the load on the motor is same, the motor has to supply same torque as load demands. So the motor react by increasing its slip to compensate decreasing in torque due to R2 and maintains load torque constant. So due to additional rotor resistance R2, the motor slip value will be increases, but the speed value will be below the normal value which can be achieved. Another advantage of this method is that the starting torque of the motor increases proportional to rotor resistance. Okay, proportional means it is inversely proportional to rotor resistance. Okay, so here what we have to do, this is the graph, this is the characteristics curve. Okay, so in x-axis will be speed n, y-axis torque t. Okay, so this is my 0 point. Okay, this is my 0 point, and at this point you can set it 1500 rpm, that is synchronous speed. Okay, here there are three types of torques are produced. One is starting torque 1, 0, starting torque 1, and maximum torque. Okay, this maximum torque, can I mark it as this dotted line? Okay, this dotted line. Okay, if you give the value of the normal R2, okay, if you apply the normal, because we know the torque is directly proportional to slip divided by R2. Okay, slip divided by R2. So here with the normal resistance, rotor resistance, which will be available in the machine, so during that time, okay, during that time, okay, you get SDA speed value like this. Okay, like this. This is the normal value R2. Okay, so if you increasing the R2, the torque value will be decreases. You see, it will be slightly decreases. So from the same NS, again we are taking R2. Again you will get a curve type. Okay, this value, this value will be with respect to additional resistance. We can say R2 dash. Normally, because we have to increase the torque, so to increase the torque we have to add resistance. So R2 dash value is very much greater than R2. Okay, R2. So this is the torque speed curve of rotor resistance control of induction motor. Okay, induction motor. Okay, the main disadvantage of this method, the large speed changes are not possible. Okay, this is because of large speed change, a large resistance is required. Okay, it will be introduced in the rotor, which causes large rotor copper loss. And second one, this method is not at all suitable for screw cage motor. And third one, the speed above the normal value cannot be obtained. Fourth, there will be large power losses due to I square R losses, because we are adding the resistance. So if the resistance value will be increases, then copper losses will be more, and the sufficient cooling arrangements also not required, and due to power losses the efficiency will be low. Okay, this is the drawback of this method. Okay, this is the drawback of this method, efficiency is low. Okay, okay, then second method. Okay, so this is my second method. Second method is cascade control. This method is also called it as concatenation or tandem operation of induction motor. Okay, induction motor. In this method, there are two induction motors. Okay, there are two induction motors are mounted on the shaft. Okay, you can say this is the motor number one. Okay, there are two induction motors, right? Okay, this is my motor one, and this is my motor number 2. These two motors will be mounted in the shaft. Okay, this is a shaft. Okay, this is a shaft, and one of the two motor must be slip ring. You see, one of the motor is slip ring type. Okay, this motor is having a slip ring, and this is the brushes. Okay, slip ring, which is called as main motor. Okay, the motor carries the slip ring, that is nothing but main motor. The second motor is auxiliary motor. Okay, the second motor is auxiliary motor. This auxiliary motor is having a slip ring. Okay, the first motor is a main motor, it's having only slip ring. Okay, no brushes. Okay, but in second motor it's having a slip ring but brushes. Okay, this is the brushes. Okay, but in main motor no brushes. Okay, only slip ring. But in auxiliary motor, what it is? slip ring and brushes, both are available. Okay, the main operation of this method, the stator of the main motor is connected to the three-phase line. Okay, it's connected to the three-phase line RLB. Okay, while the supply of this auxiliary motor is driven, okay, at a slip frequency Fs from the slip rings of the main motor. This is called cascade. Okay, this is called cascade. Cascade means it will be in a series connection. Okay, if the torques produced by both act in the same direction are called cumulative cascading. Okay, if the torque produced by both act in the, if the both the torque, because one motor will produce torque, another motor will produce torque, these both the torques will be acting in same direction, then it is called cumulative cascading. If the torque produced are in opposite direction, then it is called differential cascading. Okay, if both the motor, okay, main motor and auxiliary motor torque in same direction, then it is called cumulative. Okay, cumulative cascading. Okay, cumulative cascading. If the main motor and auxiliary motor having a torque with this in opposite direction, then it is differential cascading. Okay, differential cascading. Okay, differential cascading. Okay, now we'll see the derivation. Okay, now let Pa is the number of poles of main motor. Okay, Pa, and Pb is the number of poles of auxiliary motor, and F is the supply frequency, N is the speed. Okay, this is speed. Now we have to set N S. Okay, NS is the speed, synchronous speed. Okay, NS for A motor. NS for A. We know that N formula, NS equal to 120 Fs by P. Okay, this is supply frequency Fs. 120 Fs by P for A motor, PA. Okay, and the speed N. Okay, this speed N is same for both the motors, are mounted on the same shaft. Okay, therefore, okay, we know that slip SA equal to slip for A motor, because A motor is NSA minus NR by NC, because NR is the rotor speed. Okay, this is NSC synchronous speed, and NR will be the rotor speed for both the motor. Okay, both the motor you have to use same notation, both motors. Okay, both motor you have to use the same notation. Okay, and in terms of frequency of, because in one motor the frequency of induced EMF will be in there. Okay, the frequency of rotor induced EMF for motor A, FA equal to SA into FR. Okay, which formula we have used? Frequency of induced EMF Fs is equal to S into Fr. Okay, this formula only we are applying here. Fa equal to SA into Fr, where Fa is the frequency of rotor induced EMF of A. Fa is the frequency of rotor of motor A. Okay, then like that for motor B. Okay, these are the formulas for for motor B. Motor B, what is the formula? NSP equal to 120 into by P PB. Okay, PP. Okay, into Fs. Fs both are same. Okay, both are same. Okay, both are same. Okay, so here you can write 120, because the frequency applicable to motor A is same applicable to motor B. Okay, then we know that FA we can write FB. Okay, this is frequency of motor B, right? FB. Okay, so what we have to do, instead of 120 we have to write FA by P equal to 120. Instead of SA you have to write SA FR by PP equal to 120 FR take, and FA we already know, minus A minus N divided by PP into NSA. Now on no load, the speed of the rotor B is almost equal to synchronous speed NSP. Okay, NSP. Okay, then for for NSP equal to N R, we can write N R. Okay, N R equal to 120 into NSA minus N divided by NSA into FR by PP. Okay, so which is equal to 120 FR by PP 1 minus by okay 120 NS by A. Okay, then N equal to 120 FR by PP into 1 minus N by, what is NSA? 120 Fs by PA. Okay, then again we can write N equal to 120 Fs by Pp into 1 minus N A by Fs. Okay, therefore Nr equal to this Nr equal to 120 Fs by Nr equal to 120 Fs by Pa plus P. Okay, this is the derivation of cascade control in three-phase induction motor. Okay, this method is always having some disadvantages. It triggers two motors, which makes it expensive. Second point, it is smooth speed control is not possible. Third one, operation is also not complicated. Fourth one, the starting torque is not sufficient to start the starter. Fifth one, said to be operated, that is PA equal to PP. Thank you.